Hi, my name is Pouya Asadi, and I'm a postdoc at University of California, Santa Cruz. And today I'm going to tell you about cogenesis of baryon and dark matter asymmetries in a UV freezing mechanism. This is based on this paper in collaboration with these great people. I want to highlight Marianne Moore, a student at MIT right now who is on the market this cycle. So we have a lot of evidence for the existence of dark matter from observation across many different scales, from CMB to large scale structure to galaxy clusters and individual galaxies. In all these systems, we have gravitational evidence for dark matter, but we really don't know anything about its non-gravitational interactions with us. And we want to understand that. That's why we build model for it, and that's why we do search for dark matter. But we do have a lot of different models that can fit the bill and give rise to a viable dark matter option. It would be nice if we had a guide for dark matter model building, something to orient us, something that tell us what some new constraints for dark matter model building. And a very great guide that I think actually has not gotten enough attention, the attention that it deserves, is the matter coincidence problem. What do I mean by that? The matter coincidence problem refers to the fact the energy density of the visible and dark matter are very close to each other in our universe. They are within order one of each other, whereas a priori we expected them to be orders of magnitude different, the same way that photon and proton number densities are orders of magnitude different. To actually sharpen how big of a coincidence this similarity is, let me remind you some basic facts about these abundances. The matter energy density is proportional to the proton and neutron masses, which is in turn proportional to QCD scale, which is in turn set by dimensional transmutation and is exponentially sensitive to a parameter in UV. So we change that parameter by a factor of order one, and the visible matter abundance could change by orders of magnitude, 2, 3, 4 orders of magnitude in each direction. Same with the dark matter. The dark matter mass could span decades, a long range, and its energy density hence could actually span tens of orders of magnitude. Yet these two seemingly uncorrelated abundances that could be anywhere within like orders of magnitude end up being right on top of each other. This is a very huge coincidence. This is a curious pattern that on its own does not prove that these two things are correlated. It could be coincidence, but if it's a coincidence, it's really a hell of a coincidence. It's a curious pattern, this similarity that you don't expect to see on its own out there in the wild. If you see that, if you see something like this, you're prompted to ask, well, there is something that is putting this thing together, something that is giving rise to this. It's a naturalness problem, and I think it could actually guide model building for dark matter. Now, to further highlight the importance of this point, let me remind you that this similarity of abundances is the only hint we have and the only empirical evidence we have for the existence of a portal between dark matter and a standard model. All the searches we do for dark matter, they look for some portal of an interaction between dark matter and standard model, and this similarity is the only reason for this. So if we come up with a model that can explain this, the model could actually drive the experimental program for a long time. Now, what I want to also highlight, or actually what I want to make a distinction about, is what I call a coincidence model, solutions to the coincidence problem, and cogenesis models. And the difference is essentially on how generically we get the ratio of the two abundances of visible and dark matter to be order one. By cogenesis model, I mean a model that generates dark matter abundance and baryon asymmetry at the same time, but it doesn't guarantee that the ratio would be order one. In fact, the ratio may be order one only on a small measure zero part of the parameter space. Then we have to actually come up with dynamical reasons why the universe picks out that like measure zero part of the parameter space. And that I would call a full solution to the coincidence problem. That said, even though cogenesis models are not really honest to God complete solution to the coincidence problem, they're a step in the right direction. And that's what I'm gonna try to do in this talk. I'm gonna try to put forward a UV freezing cogenesis model. Now, there is a bit of a history there. When freezing was put forward very early on, people tried to put forward the model of freezing, a cogenesis model based on freezing. Um, but turns out there are a lot of actually limiting factors, and it's not a straightforward thing to do. And actually, it was very recently that people came up with some models of freezing cogenesis. And we actually now want to actually put forward the model of UV freezing cogenesis. Essentially, this is an attempt to give credence to UV freezing as a mechanism of dark matter. Based on all the discussion I had for importance of coincidence problem, I think I would give more credence to dark matter models that can explain this coincidence problem, or at least can be embedded in a cogenesis model. And that's what I'm trying to show that UV freezing actually passes that bar. So let's just jump into the model. We have here, I'm showing the Lagrangian, the new pieces in the Lagrangian. We have the Higgs and the left-handed leptons in a standard model, coupled to a right-handed heavy neutrinos. This is a usual neutrino portal that connects us, a standard model, to a set of dark particles. Chi is a fermionic dark matter, and phi is a dark mediator. And the coupling, we call it lambda. We'll come back to that. All these new particles, dark matter, the mediator, and the neutrino portal, they have their own masses. And we also introduce this new particle eta, and we call it dark sync, and it's very light fermion. It couples to phi and chi. And you will see why we call it dark sync. It actually plays a vital role in our scenario. Now, this Lagrangian you can show has a few different U1 symmetries. We can choose them to be the U1 hypercharge of a standard model, dark U hypercharge equivalent. That could also be gauged with a little bit of tweak. And we have lepton numbers, some visible lepton numbers where only the standard model L fermions and the N's, the new neutrino portals, are charged under, and some dark LX lepton number. Now, when the neutrino portal particles are massless, L plus Lx, that extended lepton number, would be a symmetry of this Lagrangian. So the extended lepton symmetry is broken by the Majorana mass of these neutrinos. And we're going to assume that this mass is very large, larger than the reheat temperature. So this extended lepton number is very badly broken. So in this setup, and in this part of the parameter space, I will show that we get a working UV freezing cogenesis models. And these are the ingredients that allow us to get the right abundances for dark and visible matter. And I'm going to quickly go through each of them and what they do. Hopefully, I'm not going to actually go through the calculations. Just going to sketch the calculation that needed to be done. But I'm just going to highlight the ingredients that give rise to a working cogenesis setup here. So let's start by talking about the processes that give rise to asymmetries and populated dark sectors and the lepton number violation, L and V. So we have a lot of 2-to-2 processes with some standard model particles going to dark particles chi and phi. And they populate the dark sector. In freezing setup, we start with nothing in the dark sector and we populate them like this in this setup. But also, there can be loop diagrams like these guys that interfere with the 3-level 1 and give rise to the required CP violation that allows us to source some asymmetric abundance as well. This is the usual terminology. Asymmetric abundance means more matter over antimatter, whether dark or visible. Now, all the processes that are relevant for us are mediated with the heavy Majorana neutrinos, and since they are heavier than the reheat temperature of the universe, and we integrate them out, the portal interaction is non-renormalizable, and this is what people call UV freezing. Now, some of the processes we have actually are lepton number violating. They're proportional to the Majorana mass of these heavy neutrinos. And that lepton number violation is actually very crucial. One of the actually limitations of the original models of freezing cogenesis was that when you have a conserved U1 between the visible and dark sector, like there were limitations because of unitarity bounds. You could not actually generate that much asymmetry in for baryons. But the existence of lepton number violation actually allows us to circumvent those limitations that I'm not going to go into more detail of. It also these lepton number violation means that the number of dark matter asymmetry and baryon asymmetry we have, they can be different. So the dark matter mass that could give rise to the right abundances could actually span a long range and is not limited to a narrow window near the proton and neutron mass. Now, we write down the Boltzmann equation. We write down all the processes, 2 processes relevant here for the Boltzmann equations of the visible and dark matter asymmetries, and solve the Boltzmann equations numerically. But I'm not going to just go into the details of that, just telling you that we have done this calculation, and I'm just sketching the qualitatively important ingredients in this setup. So these are the processes that generate the asymmetry and populate the dark sector. Now, something important that happens is what we call wash in. For that, let's actually look at the evolution of the dark matter abundance, both symmetric dark matter and asymmetric dark matter abundance. Here I'm showing the ratio of the dark bath temperature over standard model temperature. And that temperature is a proxy of the symmetric abundance of dark matter. And time goes to the right here. As is the characteristic of UV freezing models, very close to the reheat temperature, we see that the dark symmetric abundance jumps up to some value and gets saturated here for different values of the portal coupling. And the larger the portal coupling, the more populated the dark sector will be. Now, this is the symmetric abundance that goes into the dark sector. What about the asymmetric side? Here I'm showing the asymmetric baryons, the solid lines, and the asymmetric dark matter abundance, the dashed lines, as a function of time. Now, again, you can see that the asymmetries grow very close to reheat temperature, and they actually saturate there. But something funny happens when we go to large values of lambda. Let's look at the red lines here. The dark asymmetry gets populated and grows, and so does the visible asymmetry. But at some point, we will have too much dark asymmetry such that the washout terms in their Boltzmann equations become relevant. In Boltzmann equations for asymmetric abundances, we have source term and washout terms, the terms that are proportional to the asymmetry themselves, and they could actually wash away the asymmetry. When the asymmetry in the dark sector becomes too large, it washes it away and it actually brings it down a lot. And while it does that, the visible asymmetry actually picks up pace and it goes up. This is in the strong washout regime. And this is a way for transferring asymmetry from dark side to the visible side. We can generate the two asymmetries together, but we have in parts of parameter space more symmetry generated in the dark sector, and then it gets transferred to the visible sector. And this transfer through washout terms is referred to as wash in. And since we are relying on the dark asymmetry to bring in asymmetry to visible matter, we call it the dark washing. And it actually opens up a very wide mass range for dark matter, viable mass range for dark matter in this setup. So this was the second important and new, qualitatively new ingredient in our setup. Finally, we should talk about the dark sink thing. So while we populate the asymmetries in the two sectors, we also generate a lot of symmetric abundance for dark matter, and it actually will be dominating the asymmetry in the dark sector, and it overcloses the universe if it stays around. And this was actually one of the main problem in the original freeze-in models. One thing that actually helps with this problem is if we have relics that the dark matter, the symmetric abundance of dark matter could annihilate to and freeze out. So that's what those eta particles were doing for us. The chi masses freeze out into, the chi particles freeze out into eta, and eta is a light fermion, redshift like radiation for longer, and its energy density dilutes. And that allows us to actually deplete the symmetric abundance of the chi's that is dumped into the eta bath. Now, these eta particles, since they are light, in principle, they do contribute to delta N effective. Unfortunately, the contribution is actually in all of our parameter space is not that large to be detectable at even future CMB searches like CMB stage 4 if it were to happen. So let me actually put all these different ingredients together and summarize the scenario. We start at the reheat temperature with 0 symmetric and asymmetric abundance for the darkest stuffs and 0 asymmetry in a standard model after baryogenesis. And the portal mass, the portal neutrino masses are heavier than the reheat temperature. Then through scattering processes, we populate both the symmetric and asymmetric abundance of dark matter, and we also generate asymmetry for baryons. And because the extended lepton number is broken, we can have different number densities for leptons and dark leptons, and that means we can actually, the mass of the dark matter could span a large range while explaining the right abundances. The existence of washing terms also allow us to get a large hierarchy between the number density of visible and dark matter, which again translates into a large range of dark matter masses that could allow us to get the right abundances. After these asymmetries are generated, things pass on for a while. The phi particles decay at some point. Then at some point, the chi particles freeze out into the bath. And eventually also the electroweak sphalerons actually freeze out, and the B minus L asymmetry that we generated turns into separated B and L asymmetries. And these two last steps could actually happen in different orders. I'm not going to have time to go into all the details of the parameter space. There's just many parameters here, but happy to actually talk about these in the Q&A part. But the upshot is that we will find that our setup gives rise to the right masses for dark matter and baryon asymmetry in a wide range of dark matter masses. And this is a cogenesis setup. So with that, let me summarize quickly. I just wanted to highlight that we should care about the coincidence problem. And if you ever forget why we should care about that, just remind yourself or ask yourself, why do we even look for dark matter? Why do we even think dark matter interacts with the standard model non-gravitationally? In this setup, we put forward a cogenesis model. It's not a full coincidence problem solution, but a step in the right direction. And our setup was based on UV freezing mechanism. And it had ingredients that included a scattering, not decay, lepton number violation, washing, and a dark sink for taking away the symmetric abundance of dark matter. The model, unfortunately, doesn't have visible detectable signals right now. But if you want to turn it into a full coincidence model solution, we need to correlate the dark and visible masses. And hopefully that in those setups, we will be able to have a detectable signal. And that's something I would like to explore in future works. Thank you for your time, and I want to thank organizers for putting this nice workshop together.